artificial intelligence will completely transform our world. But what is AI? Why will it affect you? And how can you and your business survive and thrive through the AI revolution? Welcome to AI and You. Here is your host, author, speaker, and futurist, Peter Scott.
Hello, and welcome to episode 227. I know after last week's episode, you may be thinking, is that really him, or is it Notebook LM trained on his voice? Well, there's no way that I'm going to let AI have all the fun. So unless it one day becomes pointless or archaic for humans to record podcasts, this one will continue to be all me. Today, I'm going to be talking about cognitive architectures with John Laird. Cognitive architecture sounds a bit dry, but if I say gateway to artificial general intelligence, that may be more accessible. This is where our models of intelligence rise to levels higher than how neurons talk to each other. We're going to talk about this in terms of Kahneman's System 1 and System 2 thinking, and we'll explain those if you're unfamiliar with them. We'll talk about decision loops, models of the mind, symbolic versus neural models, and how large language models do reasoning. John is Principal Cognitive Architect and Co-Director of the Center for Integrated Cognition. He received his Ph.D. from Carnegie Mellon University in 1985, working with famed early AI pioneer Allen Newell. He is the John L. Tishman Emeritus Professor of Engineering at the University of Michigan, where he was a faculty member for 36 years. He is a Fellow of AAAI, ACM, AAAS, and the Cognitive Science Society. In 2018, he was co-winner of the Herbert A. Prize for Advances in Cognitive Systems. So let's get into the interview. John Laird, welcome to AI and You. It's a pleasure to have you here. Your work on cognitive architectures goes back at least to, I think, 1986, when you were working on something called SOAR with Allen Newell and others. And maybe we could start there, although if I should start earlier, then please correct me, but I definitely want to get on to SOAR.
So my thesis as a graduate student at Carnegie Mellon was on SOAR, which I completed in 1983. So we were working on it before 86. And you could say that I've been working on my PhD thesis for the last 40 years. So it's been...
Well, a lot of people who haven't gotten the PhD yet hate to think that they've been working on it almost that long.
Yeah, but it's been a fun journey, and we continue to learn things all the time. So it's been a lot of fun to do this work.
So introduce us to that work, please.
Sure. So the idea behind cognitive architecture is that we can think of different levels of processing in the human mind and the human brain, and also in AI systems. So we have levels down at the neurons, which are happening, pretty quickly. But if we come in at a level above that, which is where there's sort of the most deliberate decisions being made, and according to a lot of theory in cognitive psychology, that's at about the level of 50 milliseconds. So every 50 milliseconds, you're making a decision. It's sometimes a very small decision, like to try to retrieve something from long-term memory, or to initiate a motor action, or to change your eyes or whatever. But if we are trying to predict the course of human behavior over simple tasks like pushing buttons, or even things more extended than that, this model of saying the basic operations are about 15 milliseconds is very precise and accurate in terms of being able to predict how long people will do those tasks. It takes longer to access things in long-term memory, such as facts about the world or previous experiences you've had. It varies on how familiar that is to you right now, but that can take like 200 milliseconds. But the idea is that we are modeling at that level, or we're trying to build AI systems based on that level of processing, as opposed to what's going on at the individual neuron level or sets of neurons. Now, we, of course, accept the fact that in the brain, this level would be implemented by lots of neural structures, but we think that there's enough regularities at this level in terms of the kind of knowledge people use and the decisions they make, that it's fruitful to create AI systems that for the most part are ignoring the details of what the processing is underneath. Now, also, this is a level that's faster than something like planning. So if we look at this level by itself, we sort of call this immediate cognition, and it corresponds roughly to what Daniel Kahneman talked about as system one, which is fast and automatic processing. And that goes on when you already know how to do something. So if you're well trained in a task, which most of us are day to day in order to do speaking and understanding, we've done this a lot. So we are able to just cruise along at this level. But whenever we hit what we call an impasse, meaning that the knowledge we have about the task we're trying to perform is incomplete or inconsistent, we then sort of take a step back and we would say create the problem of getting more knowledge so that we can make a decision. And of course, we can't do that when things are going by very quickly, but a lot of times we have extra time available. So we'll go off and instead of just doing the task we're trying to perform, we will think about the task. And so that's sometimes called metacognition as well, where you're doing more processing in more detail about the problem, and it allows you to be more logical. And so that then extends out. And that's maybe where you do planning. You maybe start using analogies. You might even go off and ask somebody else for help. So we call that extended cognition, or it's related to metacognition, and it's related to what Kahneman called system two. So a cognitive architecture is trying to come up with the computational mechanisms that we can run on a computer to do these levels and produce behavior that is able to bring together a lot of different kinds of knowledge and sort of have the generality of humans. Just to take it one more step is that there's a lot of discussion about large language models and what they can do. And I would say those are going to be at that level, that system one or immediate cognition. They're not really doing any planning or problem solving. They're just predicting the next word. And so what happens is they're just chugging along, predicting the next word. And it's amazing the coherence in what they produce, but they're never sort of at a loss for what to do next because they always have another word or token to produce. And so they never take a step back and have the mechanisms for how to do more complicated reasoning and problem solving.
Wow.
Well, and one more thing is that we also assume that within these things that we have, that there's learning mechanisms that are going on in the background all the time. So one of the problems with large language models is they only get new information when they are trained. And so that takes many months for them to be trained. They might get refined through fine tuning or other mechanisms. But while you're interacting with them, they are adding information to what's called their context, which influences their behavior. But the large language model itself is never being modified. And part of cognitive architecture is to also try to develop learning mechanisms that are incrementally adding knowledge as the system, like if we have a cognitive architecture implemented within a robot, as this robot is interacting with the world, the system is learning new knowledge. One of those kinds of knowledge is episodic knowledge, which is memory of your past experience, but also it's facts about the world that you encounter. People tell you things, you discover things. And it's also what is speeding up your actual processing by being able to compile what used to be complex processing into simpler processing. So all of those things are going on as the system is behaving. So that's an important part of a cognitive architecture. It's not that it just has knowledge to perform tasks, but it's actually acquiring knowledge while it's doing those tasks.
Wow. You've given me so much to unpack, so many notes here. If we go on at this rate, this is going to be a divergent process. And my favorite kind, this is amazing. So one of the first reactions I had was you are establishing what looked like some explicit links to neuroscience here that bring in connections with the brain. I recently attempted to read Stephen Grossberg's book, Conscious Mind, Resonant Brain, and that sort of broke my brain in the process.
Well, he's brilliant, and it is a challenge to unpack what he has written, but there's a lot there.
And what you were saying about the 50 millisecond, was it milliseconds?
Yes.
With a 50 millisecond interval, irresistibly reminded me, probably quite incorrectly, of computer architectures for real-time processing and event loops. I don't know if there's any parallel there.
Yeah, I think there is. So at 50 milliseconds, we think in cognitive architecture, they're going through a cycle of making a decision using their knowledge. We call it procedural knowledge, which is knowledge about making decisions. And that it makes a decision, and that might be a decision to do an action in the world. It might be a decision to retrieve something from long-term memory. It might be an internal decision or computation, such as adding numbers together or whatever. But then it's done that, and then it comes around again and decides what its next decision is. And so we're doing that kind of loop of making decisions over and over again in sequence. And some of them interact with the world, leading to new perception. Some of them interact with the memory systems, bringing in new memories. But that's sort of what it is, like an event loop in a computer system, which is continually going forward, retrieving information from its memories, making decisions.
Right. And so this is at an interesting level of abstraction because AI and neural networks, artificial neural networks, and then large language models and transformers that are built on top of those are modeling the neuronal structure of the human brain, which we can observe. They're built on that model. And insofar as that works for humans, that's how those AIs work. And you're talking about a level of abstraction that is a bit higher than that of how the brain does this loop of processing. Right. Do we actually know how to connect in humans that level with neurons firing?
Well, there's a lot of theories about that. So let me go through some of the thoughts on this. So there have been cognitive architectures that are more at the neural level. So there's a system called SPAWN. It's been built by Chris Eliasmith at the University of Waterloo, who tries to model neurons very precisely, and that the behavior of the system comes from the neurons firing, but it does then produce behavior at this about 50 millisecond type cycle. And so you look to that, and then there's another cognitive architecture called ACT-R, developed by John Anderson and his group, and they interacted with a neuroscience researcher named Randy O'Reilly, who has neural models of different parts of the brain, and they looked at how that could connect up. Another thing we've done on this level, me together with Paul Rosenblum, Christian Lebert, and Andrea Stogo, is to try to look at many different cognitive architectures and look at similarities among them. Usually in science, it's always, how am I different than anybody else? And try to stake out your territory and make that distinction. We had some symposium where it seemed like there was a growing consensus in the community. And so we created something we originally called the standard model of the mind, but then we went with common model of cognition, which is, it's even more abstract than a specific cognitive architecture. It tries to look for commonalities among cognitive architectures. And it has a few different modules like perception, working memory, procedural memory, and declarative memory and motor systems. And it has specific connections between them and how those all send information among themselves. Andrea Stogo and his students looked at fMRI brain scans of humans solving many different kinds of problems. And they found that the kind of structures we hypothesized in the common model, there has been people who map that onto different parts of the brain, saying where declarative memory is, where procedural memory is, and perception, and so on. And if you look while people are solving these problems and seeing things and processing and doing actions, the kind of connections and the dynamics of where processing is being done in our common model of cognition seems to correspond to the dynamics in the human brain. So it's a very abstract level. And I must admit, I was shocked. I mean, you usually do science and hope that things are going to correspond to, what's in the world, especially in AI, because mostly it's theoretical, building systems, and we don't really try to model the brain. But when we saw that we did have that correspondence, it was very eye-opening. And so I think that that's another example of where we are seeing interactions between work in neuroscience and cognitive science and AI. Those sort of ideas coming together to give us a better understanding, we think, about how to build AI systems, but also a better understanding of what processing is going on in the brain and the human mind.
Understood. And to just back up momentarily to a higher level here so that listeners are clear where we're going here. You have a paper called Cognitive Architecture Requirements for Achieving Artificial General Intelligence. Just so we're clear, is the purpose of developing a cognitive architecture to be able to make a description of how cognition may be achieved, that it could be implemented in a computer?
That's our goal. I think different people have different goals, but there are cognitive architectures that are more on the neural side. And so they're mostly thinking about the neural processing, although they hope to get up. And I think Spawn is an example of where they've progressed up to what we would call cognitive processing. But there's other people who are not concerned at all about the neural level. And there's people who develop cognitive architectures for sort of subsets of tasks, not trying to be as general as everything that people can do. But I would say that my goal has been trying to understand intelligence, both in terms of, what processing humans do, but also what processing we can do in computers. And my approach for doing that has been to look into developing cognitive architectures.
For you, is it more about understanding or building?
Well, you can't build unless you understand, and building helps you understand. So it's really a loop that you come up with some initial theories about what to implement, and you build them. And then from that, you end up getting more hypotheses about what is missing is often what you discover, what wasn't covered by your theory, and what you need to add to it. But also, one of the things, so Allen Newell, one of the founders of AI, was my thesis advisor, and he advised me when I was doing my Ph.D., and I worked with him and Paul Rosenblum on SOAR project for years until he died. And one of the things he always said was, listen to the architecture. So sometimes when you're coming on a new phenomena, one of the things to do is say, you've made a bunch of commitments in your architecture already. Let's try to see if there's a new phenomena that we haven't thought about. Is that something that we can capture with the assumptions we've already made? Or do we have to go and extend our theory in new ways? And so the way we do our research is often we'll look for some new phenomena. So for example, for a long time, SOAR did not have anything that's close to what humans have in terms of episodic memory, a memory of past events. There was nothing automatically done about that. And so we looked at how to do that with the mechanisms in SOAR at the time, and those proved inadequate. So we tried to look at the architecture, saw that it was insufficient, and said, what mechanisms do we have to add in order to make it so that the system could remember its past and retrieve it and reason about it?
And was that architecture just on paper, or did anyone instantiate it?
Well, some part of my philosophy is you don't really understand something until you've got running code. So we always build, if we have a theory, then so a graduate student or a couple graduate students over the years have implemented modules that are part of the SOAR architecture that implement episodic memory. And so just to give you another example of a capability that we did not have, and a lot of these seems obvious now when you look back and say, well, how could you expect to have a cognitive architecture that didn't have this capability? Well, it takes a long time to appreciate what's missing in your system. But for example, one of the things people are able to do is mental imagery, where they can imagine situations that seem to be like images and manipulate them. And that's not the kind of symbolic processing that happens in a lot of cognitive architectures. And so it was becoming clear to me that we couldn't capture a lot of reasoning that people do and is very valuable in SOAR without mental imagery. So some of my students went off and did a lot of reading of the psychology literature and also just looked at the functionality required from the computer science side, and we built an extended SOAR architecture with that.
I think a lot of people would say, how could you expect to build a cognitive architecture with 1990 computer technology? Do you have to wait for processing power to catch up?
So, no. So to be brutally honest with myself, one of the reasons we were able to do it is we never had systems that had anything close to the amount of knowledge that humans have. And so we didn't have to have incredibly huge gigabytes of knowledge. And we didn't have, back in the 80s and 90s and 2000s and even 2010s, we didn't have access to that kind of information. And so we were able to design our systems to be fast enough then to build AI systems that were able to solve interesting problems. One of the great things was that technology we developed in the 90s now runs 100 to 1,000 times faster than it did in the 90s because of just Moore's Law. I mean, Moore's Law has started to, has peaked over the last 5 or 10 years, but at least for a while, we didn't worry too much about speeding up our system because we would just buy new computers. And so that was an interesting situation. The world has changed now with large language models and transformers, and that makes it difficult to, within my computer, run a large language model. So we do use large language models in our work, but we end up going out over the internet to GPT-4 or whatever and access it that way as opposed to having it part of our system itself.
I want to dig into the connectionist versus symbolic architectures and models here, which I also relate to Kahneman's System 1 and System 2, which we've talked about a number of times on the show. And human beings, it seems at the base, we have a connectionist architecture. We've got a neural network. And then we layer a bunch of neuroscience on that I don't understand. And then on the top of that, we can do symbolic processing. We can learn how to do calculus and algebra and other things that are also simpler, but still symbolic processing. And then sometimes we manage to learn something through that kind of System 2 thinking and ingrain it to be System 1 thinking, like learning to play a musical instrument. Boy, this is going to be a big question. Let's try it and break it down.
Let's do it.
What is the relationship between symbolic and connectionist models in a cognitive architecture?
Right. So connectionist models is sort of something from the 80s. And I don't know if what we call current neural models, connectionist models or not. That language has sort of fallen away, but whatever. So just neural models. So as I mentioned, I think that at some point we will see a unification where we see how neural models can support the kind of processing we're seeing in these symbolic cognitive architectures. So I will not bemoan the day where instead of my cognitive architecture being implemented in C, it's implemented as neurons. But right now, I don't understand well enough the kind of processing and how to organize the neural structures in order to support the kind of symbolic processing we're doing right now. Now, I point to other people who are going down that path, like Randy O'Reilly, plus Chris Eliasmith, who have their theories. They're not developed enough, or I'm not familiar with them enough or comfortable with them enough to sort of adopt them and go completely in that direction. But I think we will see a unification where we see the neural systems doing symbolic processing. Already, if you look at what a large language model is doing inside the neural network, we can argue whether or not there's symbolic processing going on. But if you look at the higher level, it is taking in words and tokens and producing words and tokens. So it's actually at the highest level, there is symbols being processed by it. And one of the things we would love to try to understand is, so for example, could I have a transformer that's part of a cognitive architecture like SOAR that is continually learning based on the structures that are going through the system's short-term working memory? And would that then be one way of doing an incremental unification of these systems? But I think that is an area of really possible advances in the next 5 or 10 years. Some people talk about neurosymbolic computing. They often don't really define what's neural and what's symbolic or what the unification of those is. For me, it would be that we would find a way to build neurostructures that implement what we call procedural memory, or what we call mental imagery or declarative memory, episodic memory. So understanding how those systems would be implemented in neural structures and all connected together. And I think that's a little bit of the Wild West right now. one of the challenges in the past and possibly the current is that the resources required to do that are really large. And so it's very difficult for individual researchers to do it. And as you mentioned, how do we avoid that level of simulation of individual neurons? So, I mean, if you have to be simulating billions of neurons, that requires a lot of computation, a lot of time, a lot of money. And so I think that we'll see whether the cost comes down and that's going to be possible, but it's a real challenge right now.
Well, again, so much to build on there. And it seems to be a big hot question right now as to when large language models do, as you say, this apparent reasoning, whether that's a real effect, whether that's an emergent effect, whether it's an imitation, or whether it doesn't matter. How do you unpack that?
So there's been a lot of research in the last 6 months or year on how well large language models do very simple reasoning. So Rao at Arizona State, I can't pronounce his whole name, but he has done a lot of research on simple blocks world puzzles and shown that they're very challenging for large language models. What large language models do is if they've seen that specific problem in their training set, they'll be able to solve it because they just are sort of retrieving it, or if they've seen something very similar that they can map onto it. But if you get outside of what they were trained on, they're lost. So they just don't have, they are drawing on everything they've seen in order to say, well, what's the most likely thing, token, symbol to produce next? But there's no internal reasoning. It's very easy to ascribe to them when you watch them. And I do this all the time. I watch it producing text and it's like, it must have an internal model that it's reasoning over in order to produce that text. But it doesn't. It has activation within the neural structures that is leading it to produce something versus something else. But it's not creating intermediate representations. Say, it's not doing internal planning over possible future states in order to decide what to do. So the other way to talk about it is if you get the right answer in an extended reasoning from one of these systems, it's just that was what it got trained on. And if you go outside of that at all, you probably won't get the right answer. So it's sort of lucky that you get the right answer because it's had the right experiences in the past. But one of the things people are able to do is you're able to give them a new problem and they can reason through it step by step. And what you notice, and you're going to get to probably, is that the language models are the system one, very fast reasoning. The time it takes to produce one symbol versus another does not change at all. But if you ask someone to solve a problem and they know it very well, they'll just spit out the answer. But if you ask them something they haven't, they'll sit there and think. And what is thinking? That is taking time to consider alternatives. So I do Wordle every day, the game where you're trying to come up with what are letters to guess to get a final word. And at the beginning, I've done it enough that I've got specific words that I use in specific situations. And so I'm very quick at the beginning in order to generate words. But then I'll get a new combination of what letters belong in specific situations, places, and which ones might belong anywhere. And I have to, at least I feel like what I'm doing is I'm trying to generate words that are consistent with that. And I might try to generate a lot and then pick between them. And we don't see that's the sort of thing that language models are doing at all.
Mm-hmm. That was great. I do Wordle as well. And so it's the same thing. It's automatic to begin with. This is almost equivalent to opening moves in chess.
Exactly.
But, my first word is irate. And if none of those match, my next word is soupy. And those are automatic.
Giving away all your secrets.
Yes. Well, it's not a competition, fortunately. But then I start thinking, now, if I give that task to ChatGPT, it will swear up and down that it knows what I'm talking about and how to play. And yet, as I go through it and I say, I am thinking of the word, and here is how I'm going to encode my answers with letters representing the colors of the squares. And it say, yep, I've got that. And it will make fundamental errors. And I say, no, you're wrong about that. It's getting better. It's not as bad as it was 2 years ago, but it's still awful. a child would know that it was making a mistake. And yet it's like it is reacting automatically. And that's one of the few ways I know of exposing its weaknesses.
Well, it also is every answer happens at the same time. It's it's just as fast. It's never like it pauses.
Right.
Then a better answer comes out because it's never generating these internal possibilities. It's all that it's doing is sort of this huge match against everything it's been exposed to. And it just pushes out the next word.
What human beings call thinking. I have to think about that.
I would agree completely. Yeah. So that's what we haven't seen. People are clearly, it's an open area of research, but their work so far suggests that what is productive is to have large language models as parts of other systems. So other systems that might use more classic AI planning and problem solving that then uses the large language model to generate possibilities, but that are then verified by the more logical reasoning of more traditional AI systems. So anyway, I think this is going to be an area of future research, productive future research over the next couple of years.
Thank you. I want to move on to something that you were talking about earlier, continuous learning. Human beings quite clearly do this, or at least the moment they stop doing that, they don't have much of a future. And large language models patently don't, because we talk about billion-dollar training phases. And this is a huge problem if you want them to be up on current events, for instance. But more than that, it's quite obviously exposing a fundamental difference between them and human beings. Now, in human beings, there are all kinds of things we do or ways that we behave and react that expose big differences between us and computers, like optical illusions. But one of those is sleep, which is fundamental to us and every other creature with higher order neural structures. And I was wondering, what are your thoughts on the role of sleep in human beings? And do we need something like that, or can we learn from that in our cognitive architectures?
So I've not studied sleep very much. I mean, I've looked at some of the research that shows how people degrade without sleep, but that's on performance as opposed to necessarily on learning. Just that the less sleep you get, you have a cycle and a 24-hour cycle. And as you get extended out, your performance really degrades when it's 2:00 in the morning. But in terms of learning, there are theories that replay during sleep is critical for both filtering and establishing memories, especially episodic memories, because it's clear that most of us do not have memories of every moment of our lives, and that it would be probably too much for us to have that, and that instead we have temporal summaries of things, and we have even at different levels of abstraction. So I can say, I was on a podcast today between noon and 1, and that doesn't require me going into all the details of everything I said and everything you said. So we can do that, and I might remember very poignant things that happened during this and be able to recall those. But in terms of having like a videotape memory, most of us don't have that. Some people seem to have something close to that. And that the argument is that sleep is useful for filtering out what was not important. I don't know. I don't have a theory on that. We don't have that as part of our cognitive architecture capabilities right now. I'm willing to be uncertain and to learn more down the road.
That's the end of the first half of the interview. Obviously, we're dancing around the edges of some pretty sophisticated thinking, and just getting a glimpse of how sophisticated this research is wild. You're welcome to use my Wordle opening moves, by the way. In today's news, ripped from the headlines about AI, Meta's new AI studio lets anyone in the US, create an AI version of themselves for Instagram. Essentially, it's like the digital clones we've been talking about for years, and possibly even their foray into the AI girlfriend/boyfriend market. You can customize the character from a typical sort of "you are such and such" LLM prompt and instruct it as to its personality, tone, purpose, and so on. The more obvious use case for it is celebrities using it to put out versions of themselves with different quirks to talk to their fans, but maybe some more useful functions will emerge over time. Next week, we'll conclude the interview with John Laird, when we'll talk about relationships between cognitive architectures and artificial general intelligence, where explainability and transparency come in, Turing tests, where we could be in 10 years, how to recognize AGI, metacognition, and the SAW architecture. That's next week on AI and You. Until then, remember, no matter how much computers learn how to do, it's how we come together as humans that matters.
That's all for this episode of AI and You. Please leave a rating and comment and share with your friends. Get the book Artificial Intelligence and You and see more videos and articles at aiandyou.net. That's aiandyou.net, where you can also send us your questions. Thank you for listening.